Hello and welcome everyone to a proper lab update where we talk about boards, we stay inside in the lab, and yes, very classic. Today I will talk about 3 gadgets that either are for sale or will be for sale or will not be for sale, we will see. And that is number 1, a tool, a board that lets you connect to your various open inverter boards via CAN and presents the parameters via the well-known web interface, or actually an updated version of it. We will have a look at that. Then second item is once again the BMS. I have polished it up a bit, and we will take a brief look at that as well. That's already for sale. And then last but not least, UIs STM32 CCS board. He calls it the Foci or something. And yes, I have equipped the ladder with a new firmware that also lets it talk to the gadget mentioned first. It will all come together in a second. Let's swing over to the desk. Let's first look at the nice and polished up version. This is the new ESP32 board. And it's very simple to use. It's got a 12 volt inlet over here, it's got CAN over there, and then optionally for future use it's got an SD card slot, which this one does not have because I screwed up the part numbers. This is not my work. Actually, a lot of what I'm showing today is not really my work, but I've stolen it from I think VoltLock. I will link in the repositories down below, and the original name is ESP32 CanLight, which I've left on there because I didn't want to come up with a new name for it. I've also stolen this 3D printed box because I can't do 3D printing. Ordered this off JLC PCB just as well as a PCB, and this just clicks in here and then makes it a very nice gadget. And we can access all the 12 volts and the CAN and the SD card through this slot down here. Let's look at it in action. Here I've built up a small CAN network consisting of the CCS controller that I'm currently debugging, the ESP32 CAN board, and sorry about the mess, it's hard to even see anything here, and a very old inverter board. Here, version 3. The first version 3 board that ever was, hand-sold it. And that's also part of the CAN network, and we will take a look at accessing all that. So we start out with the new CCS controller, which now has open inverter style values and parameters. It's not very fleshed out, I just did it last night. That's all there is. Basic communication parameters, basic charging parameters, and these will all make sense soon. And yes, we can also update the firmware here. We can add CAN mappings and all that. And then I've kind of arbitrarily given it node ID 22, and then on node ID 1, I will just we are now connected to an inverter, and that's the version 3 board that I showed you earlier, and it just continuously updates, and it's got all the facilities it always used to have, like we have the plot, and yeah, this interface, this user interface we're seeing here is also not my work. It's done by Christian, I forgot his last name, actually quite a long time ago, and I decided to swap it in for the legacy style user interface. Yep, so here comes our plot, works just as well. There's one limitation of the CAN interface, of course. With the UART 1 Mbit interface we could do like real-time updates. We could see motor currents in real time and all that. That is not going to be possible with this CAN interface because it's just too slow for that. But for most things that would be relevant like speed and pot and temperatures, this is by far quick enough. Then there's another example of it being used down in the shed, and that's with the BMS. And yeah, at the same time we can talk about things that happened to the BMS lately. Various cell voltages is currently balancing away. And you see I can also switch between node ID 3 and 4. Node ID 3 is sort of the master or main node, and then node ID 4 is the one subnode. You might remember this from the last video. There's 2 boards on a 32 cell battery pack, sensing 16 cells each. Yeah, while we're here, let's take a look at how the BMS has evolved. Not much happened here. Yeah, we got balancing modes now, so we can tell it to not balance at all, to only bump up low cells, to only dissipate high cells, or to do both. And so they meet in the middle. We can choose that now. We can choose the voltage at above which it starts the balancing. We can select a time, which has to since the last current draw until it starts balancing and SOC estimating and all that, because it has to wait for the cells to reach their true idle voltage. I think usually I set this to 1 hour. Here we go. Then we've got basic voltage cutoffs. So the BMS itself has no handle on the current. It can just measure it, and then it will output current allowances via CAN. It can't limit the current draw by itself. It's just monitoring and telling other devices what they should and shouldn't do. So here we've got minimum maximum cell voltages. It's a lithium iron phosphate pack, thus low values. We've got a maximum charge current and a maximum discharge current. And then here we can configure a charge curve. As we all know from the OEMs, they kind of start very quick and then taper off quite even quicker. Same we did here. From 0 to 10% we allow 100% of this charge max. From 10 to 20 still 100%, 20 to 30 100%, and then we start tapering off 90%, 80 and so on. And now these limits are just multiplied onto this charge curve. So if we are, somewhere here in the charge curve, and at the same time we are hitting the upper cell limit, that would also limit the charge current even further. And same goes for the measured cell or pack temperature. There's no value here for 100% SOC, because at 100% SOC we are charging not at all. Nominal capacity, this is something you enter manually for now, and later on I'm hoping the BMS will find out by itself how much capacity there is left in the cells, or the lowest cell or something. And then here we can configure 10 points for SOC estimation from voltage. Again, this is for lithium iron phosphate. So after resting for this 1 hour that you configure in the idle weight above, it will take a SOC estimate. And well, next time it sees current again, it will do the usual Coulomb counting to calculate the SOC. We've got a current sensor on there. It's got an offset gain. It's a differential current sensor, so it's got 2 outputs. One usually sits at 2.5 volts, the other one swings around as there's current. We can select various temperature sensors. And I think all that has been on here before, also in the last video. Also the spot values haven't really changed much, I think. We can see the charge limit, 36 amps, and we are roughly at 80% state of charge. Is that what we configured? Let's check. So 30% of 120 amps, that's around 40 amps. So that is mathematically correct. Let's go over UIs Sport. UIs is a developer from Ingolstadt in Germany, and he has crafted the first open source fully open source implementation of a CCS charge controller. So it means open hardware. The board you're seeing here is open, and the software also is. Right, so what we see here is the CCS controller. It's got an STM32 that is also used on the inverter on the top here. And then it's got a QCA 7000 chip that is used for power line communication, the silly power line communication of CCS. And you can see it's got various helper outputs as well. So on the top side we've got the sort of vehicle connection, so it's the 12-volt power supply, and then it's got the CAN connection, over which we tell it what sort of charge current we want and state of charge of the battery and stuff like that. It can light up some LEDs for various status messages, and it can read a button. And then on the bottom here we've got all the connections that go to the charge port, so we've got various temperature sensors that we can read to make sure the contacts are not overheating. We've got the locking motor, which drives a pin into the connector so you can't pull it out. It can measure the high voltage on the port directly, if so wanted, and most of all it's got the CP pin, which has the power line comms on it. So I don't know how this board will be distributed. It's a bit more challenging to put together than the other ones because it's got this QCA chip, and JLC PCB doesn't have QCA 7000 chips in stock, so they cannot be populated, and it's quite ugly to populate it by hand, so we will need to find some solution for that. And then we will see which sort of shop it turns up in. I think that's it for today. So this gadget, let's shed some light on it, will show up on the Open Inverter shop. Lets you do away with the Wi-Fi modules that's on the boards, which will have higher connection speed but often have a poor connectivity because they're inside a metal enclosure. The BMS is already on the shop, and now in addition I will at least soon be offering this 3D printed enclosure. Again, not my work, a good friend of mine has designed that one. So it's taking 4 bolts. First you put in the board, then you put this one in, and then you can put 4 bolts on the top, and you can bolt it down wherever with these little noses here. Right, I think that's it for today with the new PCB update. Hope you found that somewhat interesting. Thanks for watching, see you next time, bye.